In this lecture, I cover dependent voltage and current sources. A dependent voltage source is a key component in operational amplifiers, which we will cover next. The objective of this lecture is to describe how dependent voltage and current sources function and explain how they're treated when analyzing a circuit. The value of the voltage or current of a dependent source is determined by the value of some other parameter within a circuit. In this course, the parameter is the voltage across or the current flowing through another component. In a number of circuits, these other parameters may allow us to sense changes within a circuit or environmental changes. For example, there is a component called the thermistor. Its resistance changes as a function of the ambient temperature. If we had a dependent voltage source whose magnitude was dependent on the resistance of the thermistor, then we could directly measure the voltage across the dependent source and calibrate it to the temperature in the room. Other parameters that are used are the amount of light shining on a component, which is used in a number of photosensors, and the mechanical stress applied to, say, a strain gauge or a MEMS sensor, where MEMS means micromechanical electrical sensor. These components can be used to measure the changes in atmospheric pressure, or in the case of a MEMS accelerometer used in your car, can figure out when you've had a very sudden stop, like you've been in an accident, and allows the circuit to then deploy the airbag. There are a number of components, electrical and electronic parts, that we model as dependent voltage and current sources. One example that we will discuss in the next lecture is operational amplifiers. Others include transistors, bipolar junction transistors or BJTs, and metal oxide semiconductor field effect transistors or MOSFETs. MOSFETs are the dominant transistor these days used in integrated circuits, where integrated circuits means that we have anywhere from 10 to a couple of million transistors on a single piece of silicon. Other components that we use that are modeled as dependent sources are voltage and current regulators, photodetectors, light-emitting diodes, LEDs, and lasers, photoelectric devices, and thermocouples and photovoltaic sources. There are 4 different types of dependent power sources: voltage-controlled voltage sources, current-controlled voltage sources, both of which use the symbol to the right, the diamond with the plus and minus sign in them. The voltage-controlled voltage source means the voltage across a component elsewhere in the circuit determines the magnitude of the dependent voltage source. A current-controlled voltage source means that a current going through a component elsewhere in the circuit determines the magnitude of the voltage in the dependent source. The other 2 dependent sources are voltage-controlled current sources and current-controlled current sources. The symbol used for these dependent current sources is the one shown on the lower right of this slide, the diamond with the arrow going through it. The arrowhead tells you the direction that positive current leaves the dependent current source. Similarly to the voltage sources, the voltage-controlled current source has a magnitude of current that's dependent on the voltage across a particular component elsewhere in the circuit, and the current-controlled current source's magnitude is dependent on the current going through another component in the circuit. A fundamental difference between dependent voltage and current sources compared to independent voltage and current sources is that dependent voltage sources generate power only when there's another independent voltage or current source in the circuit. It is the power generated by these independent sources that produce the current that flows through, or the voltage that's produced across the component, that then controls the magnitude of the voltage or current that is outputted by the dependent source. In circuit analysis, we treat the dependent sources similar to the manner that we treat independent voltage and current sources when performing nodal analysis or loop current method. However, we do not treat these dependent sources like independent sources when performing superposition. The independent voltage and current sources are turned on and off in sequence as we apply superposition. However, the dependent sources are always left on. In this example, I have two independent sources, one voltage source, one current source, V1 and I1, and a voltage-controlled current source that has a magnitude of minus 2 times 10 to the minus 3 times the voltage across R1. There are no units associated with the coefficient in front of VR1 on the voltage-controlled current source. It is assumed that you recognize that the units on the voltage-controlled current source must be in amps, and therefore minus 2 times 10 to the minus 3 must have the units amps per volt, so that when you multiply the voltage VR1, the resulting magnitude has a unit of amp. I have decided to use nodal analysis to solve for the currents and voltages in this particular circuit and determine how much current is being produced by the dependent current source. To the right are the four node equations that I found using KCL. Next, using Ohm's law, we find a relationship between the current flowing through the components and the voltages at the nodes. The equations for this are on the right. In addition, the node voltage at node A, VA, is equal to the voltage from that point to ground, which happens to be equal to V1 or 4 volts. We then substitute the equations we obtained using Ohm's law into the equations we obtained using Kirchhoff's current law, shown at the bottom of this slide. Solving for the voltages and currents in this circuit, we find that the voltage at node A is 4 volts, the voltage at node B is 6 volts, the node voltage at C is 22 volts, and the voltage at node D is 1 volt. The current IV, the current leaving the independent voltage source, is equal to minus 1 milliamp, or it's actually entering the independent voltage source and is acting to charge the voltage source, and the voltage source is actually a power consuming device. I1 is equal to minus 2 milliamps, I2 is equal to 3 milliamps, I3 is equal to minus 4 milliamps, I4 is equal to 1 milliamp. I3 is equal to the current leaving the dependent source, which is also equal to minus 4 milliamps because R3 and the dependent current source are in series. In this circuit, I have replaced the voltage-controlled current source with a current-controlled voltage source. The magnitude of the voltage of the dependent voltage source is 3,000 times the current I2, the current leaving V1, the independent voltage source. So, when applying superposition, we will only analyze two circuits. One, where V1, the independent voltage source, is left on and the independent current source is turned off. The second circuit is when the independent current source is turned on and the independent voltage source is turned off. In both circuits, the dependent voltage source, V2, is left on. When we turn I1 off, we replace it with an open circuit. As a result, resistor R4 has one terminal that's connected to the circuit and one terminal that is not, so no current can flow through it, and therefore we can eliminate the resistor R4 from the circuit that we analyze. The resulting circuit is shown on this slide. You may select whichever analysis tool you feel comfortable with in order to solve for the currents and voltages in this circuit. In this circuit, I've decided to use mesh analysis and have found two meshes and have labeled the currents flowing through the meshes I2 and I3. On the upper right are the two equations we obtain when applying Kirchhoff's voltage law. The equations on the bottom right are the equations we obtain when applying Ohm's law, noting that V1 has a voltage drop of 4 volts across it, and the voltage across V2 is equal to 3,000 times I2. Note that I can only say this because the current going through the mesh on the left-hand side of the circuit happens to be equal to I2. After substituting in the equations from Ohm's law into the equations obtained using Kirchhoff's voltage loop equations, we have the set of equations listed on the bottom of this slide. Solving for the currents flowing through the mesh, I2 is equal to 1.2 milliamps and I3 is equal to a minus 0.2 milliamps. The resulting voltage across the dependent source is 3.6 volts. Now, having solved for the voltage across the dependent source with the first circuit from superposition, we repeat superposition, turning off V1 and turning on I1. The circuit that we obtain is shown on this slide. Again, you may select whichever analysis tool you'd like in order to solve for I2, even though you used mesh analysis in the previous circuit, as long as you solve for I2 and note that the direction of current is the same in the two circuits. I have decided to continue using mesh analysis. There are now 3 meshes in this circuit, and I have labeled the current flowing through the upper mesh I1. I've continued to call the mesh on the lower left I2, and it is still equal to the current leaving V1, which is now a short circuit, and I3 on the lower right mesh. Again, the circuits on the upper right are the 3 equations that we obtained using Kirchhoff's voltage law, and the equations on the lower right are the ones that we have obtained using Ohm's law, noting that the current flowing through the independent current source, I1, happens to be equal to the mesh current I1 is equal to 1 milliamp, and the voltage across V2 is still equal to 3,000 times I2. Substituting in the equations we obtained from Ohm's law into the equations obtained using Kirchhoff's voltage laws results in the 3 equations shown at the bottom of this slide. We already know that the current going through the upper mesh, I1, is equal to 1 milliamp. I2 is now equal to 0.3 milliamps, and I3 is equal to a negative 50 microamps. The resulting voltage produced by the dependent source, V2, is equal to 0.9 volts. Taking the results that we have obtained from both of the circuits in superposition, we find that the total current leaving the independent voltage source, I2, is equal to 1.2 milliamps plus 0.3 milliamps is equal to 1.5 milliamps. The voltage produced by the dependent source is equal to 3.9 volts plus 0.9 volts is equal to 4.5 volts. As a check, we can apply the equation for the current-controlled voltage source and say that 3,000 times I2 is equal to 3,000 times 1.5 milliamps is equal to 4.5 volts. In summary, dependent sources are voltage or current sources whose output is a function of another parameter in the circuit. Voltage-controlled voltage sources, current-controlled current sources, voltage-controlled current sources, and current-controlled voltage sources are the 4 different types of dependent sources. Dependent sources only produce an output when there happens to be an independent source in the circuit. And lastly, dependent sources are treated like independent sources when using nodal or mesh analysis, but not with superposition.